You know, usually when we talk about a medical diagnosis, there is this expectation of like absolute pristine precision.
Right.
It is like engineering, you know. You break your arm, the x-ray shows that jagged white line on the radius bone, and the doctor just points at it.
They just say, well, there it is.
Yeah.
That is the problem.
Exactly. And it is comforting, isn't it? We have this deep psychological need for things to be visible, to be categorized neatly into a little box.
Broken or not broken, true or false?
Yeah. But then you step into the world of complex knowledge representation, the hidden architecture powering, global supply chains, international banking, artificial intelligence.
All of it, yeah.
And suddenly that X-ray machine is completely useless. We are looking at a diagnostic landscape that is incredibly murky.
It is the ultimate diagnostic muddy water. You are dealing with a reality where you are constantly trying to get fundamentally different, highly complex systems to talk to each other.
Right.
And the scary part is most of the time they are totally blind to each other's definitions of reality.
Which brings us to our mission for this deep dive. Today, we are decoding a massive, incredibly complex, but frankly, revolutionary standard from the Object Management Group.
The OMG.
Right, the OMG. And this standard is called DOL, which stands for the Distributed Ontology, Model, and Specification Language.
I know that sounds like a massive mouthful of corporate acronyms.
It really does. But the core idea here is going to blow your mind. We are unpacking how computers are finally learning to understand different logical languages simultaneously.
Acting as a universal translator for the digital age, basically.
Exactly, and doing it without losing their computational minds in the process. We have a massive stack of sources for this deep dive to help us get there.
We really do. We are pulling directly from the official OMG standard specifications, obviously.
The primary source.
Plus, C. Maria Keats' textbook, An Introduction to Ontology Engineering, which is fantastic for the foundational math. We also have AWS presentation slides on interoperability and some really dense academic papers from our SWIV and CURWS.
So it is a highly specialized crash course today. But the implications of DOL, they are reshaping how large-scale data systems operate behind the scenes.
We are talking about a fundamental shift in how human knowledge is mapped by machines.
But to really grasp why DOL is such a breakthrough, I think we first have to understand the crisis that made it necessary. Because right now, in the modern tech landscape, we have this modern-day Tower of Babel situation going on.
That is a great way to put it. Different communities use entirely different mathematical languages to model their systems, and it is not just arbitrary.
Right, they do it for very specific reasons.
Exactly. If you were a software engineer building a database, you were almost certainly using UML.
The Unified Modeling Language.
Yes, UML. It is fantastic for designing the architecture of a software system. It is visual, it is structural.
Okay, so that is software engineering.
But if you step over to the semantic web community, the people trying to make the internet's data actually readable by machines, they do not use UML.
What do they use?
They rely on OWL, the web ontology language, which is built on something called description logics, or DLs.
So if I am understanding this right, to use an analogy, it is like a construction site where the master electrician and the master plumber have completely different, totally incompatible blueprint formats.
Yeah, that was a good visual.
Like, the electrician's blueprint is hyper-optimized for wiring, the plumber's is hyper-optimized for pipes. You need both of them to build the house, but if you lay one blueprint over the other, it is just gibberish.
It is gibberish.
Yeah.
But it actually goes much deeper than just different formatting or different vocabulary.
How so?
Well, it's not like the difference between saying hello in English and hola in Spanish, where the underlying concept, the greeting, is identical.
Right. The real-world object is the same.
Exactly. When we talk about UML versus OWL, we are talking about fundamentally different mathematical realities. They have entirely different levels of expressivity.
Wait, let me make sure I'm visualizing this right. What do you mean by different mathematical realities? That sounds a bit sci-fi.
Well, let's look at the computer science behind it. C. Maria Keats' textbook breaks this down beautifully. Description logics, which are the foundation of the semantic web, and OWL, are what we call decidable fragments of first-order logic.
Decidable fragments.
Yes. And they are equipped with formal semantics.
Okay, I'm going to need you to unpack formal semantics before we go any further into the weeds here.
Fair enough. Formal semantics just means there is a precise, mathematically rigorous specification of what every single symbol and relationship means.
So absolutely zero room for human interpretation.
Zero. No ambiguity. If a system has formal semantics, a computer can use logical deduction to infer brand new information from explicitly stated facts.
It can connect the dots on its own.
It connects the dots, exactly.
Okay, so the computer can reason. That sounds incredibly powerful. But you also use the word decidable. You call description logics decidable fragments.
And that is the double-edged sword right there. Decidability is a mathematical guarantee.
A guarantee of what, exactly?
It means that if you ask a computer a question, like, is this specific data point true based on the rules you know? The computer is guaranteed to eventually give you a yes or no answer.
Okay, so it will not just guess.
Right. But more importantly, it will not get stuck in an infinite computational loop.
Ah, I see. So it is basically a safeguard against the machine just thinking forever and freezing up.
Precisely. Which is
Yeah.
obviously a nightmare if you are waiting for an automated system to approve a mortgage or, route an autonomous vehicle. You need an answer.
Right, the blue screen of death because it is thinking too hard.
Exactly. But here is the catch. To guarantee that the machine will always finish reasoning and give you an answer, the creators of these languages had to place strict mathematical limitations on what you can actually express.
They had to put heavy guardrails up.
Very heavy guardrails. If you give a machine a logic that is too expressive, meaning you allow it to process highly complex overlapping rules like full first-order logic allows, the machine might literally compute until the end of the universe without reaching a conclusion.
Wow. Okay, so DOL and its underlying description logics intentionally restrict what you can say to keep things moving fast.
Yes, speed and guaranteed answers over total descriptive freedom.
I get the theory, but what does that restriction actually look like in practice? Like for a programmer sitting at a keyboard?
Well, Keats' textbook gives a brilliant, very human example of this restriction in action. It is known as the aunt and mother problem.
The aunt and mother problem. Okay, let's hear it.
Let's say you are building a family tree software using the standard OWL2DL framework. You want to define the relationship has-mother.
Okay, basic family tree stuff.
Now, obviously, this is an asymmetrical relationship. If Mary is the mother of Jane, Jane cannot be the mother of Mary.
Right, time flows in one direction. Basic biology.
Exactly. Now, you also want your family tree software to automatically infer who is an aunt.
Okay, sure.
You don't want to manually type in every single aunt for every person. You want the machine to figure it out based on the other relationships.
That makes total sense. Work smarter, not harder.
Right. So to do that, the system needs to link the has-mother relationship with a has-sister relationship.
Okay, following.
The rule would be, if Jane has a mother, Mary, and Mary has a sister, Sarah, then Sarah is Jane's aunt. In ontology engineering, this is called a property chain.
A property chain. Okay, so far this seems like a completely reasonable request for a basic piece of software. You want an asymmetrical mother relationship, and you want to use a property chain to figure out the aunt.
It is completely reasonable to a human, but in the OWL2DL language, if you try to put both of those features into the system at the exact same time, the mathematics completely block you.
Wait, really? The software will throw an error.
It throws an error. It just crashes.
Just for trying to define an aunt and a mother, that seems so basic.
Because computationally, combining an asymmetrical property with a property chain pushes the underlying logic out of that safe, decidable zone we talked about.
Oh, I see. It breaks the guardrails.
Exactly. The math equations behind the scenes become too complex for the reasoning engine to guarantee it won't get stuck in an infinite loop. So the language designers literally banned that specific combination.
That is wild.
You can have the asymmetry or you can have the AND property chain.
Yeah.
You simply cannot have both in that specific OWL profile.
That sounds incredibly frustrating. And I have to imagine that if a basic family tree breaks the system, the hard sciences must be an absolute nightmare to model.
Oh, it's a massive bottleneck. The sources actually talk about biomedical scientists trying to model complex mereological relations.
Mereological. Okay, another big word. What does that mean?
Mereology is the philosophical and mathematical study of parts and wholes. The is part of relationship.
Which is basically everything in biology. I mean, a cell is part of a tissue is part of an organ.
Exactly. It gets very complex very fast. Keith gives the example of an elephant.
Okay, let's talk about the elephant.
A scientist needs to build an ontology that specifies that an elephant's tusks, the ivory, are structurally made of apatite.
Apatite, like the mineral.
Yes, which is a specific type of calcium phosphate. But standard OWL is mathematically insufficient for capturing these deep structural part-whole nuances without violating those decidability guardrails.
Wait, so OWL cannot handle the fact that a tusk is made of a specific mineral without risking an infinite loop.
Not if they want to capture the full structural complexity of how that mineral forms a tusk, no. It is too expressive a concept for the decidable fragments.
So what did the scientists do? Did they just give up on modeling the elephant?
They improvise, and it gets really messy. They end up interspersing their OWL code with first-order axioms.
Okay, what does that look like?
They write these complex, highly expressive logical rules in a totally different language, first-order logic, to capture the part-whole relationship of the appetite. And they just paste them right next to the OWL code in the file.
Just copy and paste it in.
Yeah, but because standard OWL reasoning tools cannot read those first-order axioms, the tools just ignore them completely.
So they are invisible to the machine.
Completely invisible. The complex rules act merely as informal annotations for the humans reading the code.
They are essentially sticky notes left on the blueprint for humans to read.
Yes. They are entirely useless to the machine.
Yeah.
Which, completely defeats the purpose of building an automated, machine-readable knowledge base in the first place.
Right. If the computer cannot read the sticky note, the automation is broken. Which brings me to a quote from an AWS presentation on ontology generation that we reviewed in the stack.
Oh, this is a great quote.
Yeah, there was this moment where a programmer at a database symposium was lamenting this exact issue, this interoperability nightmare, and they said something to the effect of, any one of those tools by itself is a tremendous aid to productivity, but any two of them together will kill you.
It is the defining paradox of knowledge engineering.
Any two will kill you.
Exactly. You have all these distinct languages, right? Each hyper-optimized for a specific task. AWL for fast semantic reasoning, UML for software architecture, common logic for deep mathematical proofs. But none of them can do everything.
So my obvious question, and I'm sure anyone listening right now is thinking the same exact thing, is why can't we just invent one perfect language?
Yes.
Like, seriously, why not just get all the smartest people in a room and create a super language that covers everything from UML system designs to first-order logic biomedical Mariology? Just one language to rule them all.
You would not be the first to suggest that. That was actually the dominant approach in the industry for a long, long time.
Really?
Yes. It was the search for the digital Esperanto.
Esperanto, the universal language.
Right. They wanted a single universal formalism into which everything else must be translated and mapped. They tried it with things like common logic, which is incredibly expressive.
But I am guessing it didn't work out.
It failed miserably. The Esperanto approach fails for two major reasons.
Let me guess. One is computational, and one is human stubbornness.
You absolutely nailed it. Computationally, if a language is expressive enough to handle the most complex part-whole Mariology of an elephant tusk without breaking a sweat, it is far too bloated and slow to handle simple, rapid-fire tasks like querying a basic customer database.
Right. You don't use a sledgehammer to crack a peanut.
Exactly. It would take a supercomputer to do basic arithmetic because the language is too heavy.
And what about the human element?
Legacy systems and community inertia.
Ah, legacy code.
The software engineering community has spent decades, literally decades, building trillions of dollars worth of infrastructure in UML. The biomedical community has massive, sprawling OWL ontologies.
They are deeply entrenched.
Deeply. They are not going to throw all of that away, retrain their entire workforce, and rebuild their tools from scratch just to learn a massive, bloated universal language. It is just not going to happen.
Which brings us to the fundamental philosophical shift that birthed DOL. The industry finally realized that the Esperanto approach was a dead end. We had to abandon the dream of a single universal language and instead embrace a multilingual reality.
And that is exactly what the distributed ontology model and specification language, DOL, was designed to do.
Adopted as an OMG standard in 2018.
Yes. And DOL isn't trying to replace OWL or UML. Crucially, as the academic papers on its architecture note, DOL is a meta language.
A meta language. Okay, let's hover on that. So it sits a layer above the others.
Yeah.
It is not a new language you learn to write a database in. It is a language about languages.
Exactly. It accepts pluralism. It allows for the as-is use of ontologies, specifications, and models in their native languages.
As is, so you do not touch the original code.
You don't touch it. So if you have a massive database designed in UML and a semantic web knowledge base written in OWL, DOL doesn't force you to translate them into a third language. You leave them exactly as they are.
Okay, so if it doesn't translate them, what is it actually doing?
DOL provides the mathematical constructs to create modular ontologies and to create formal, verifiable links between these different languages.
Links, so it is the connective tissue.
Right. The standard talks about alignments, module extraction, interpolations, and conservative extensions.
I want to break those down because they sound highly abstract. What is the actual on-the-ground implication of being able to link these things? Let's think back to our biomedical scientists with the elephant tusks.
That is a perfect example to reuse. With DOL, that scientist can keep their existing OWL ontology exactly as it is, maintaining all that fast, highly optimized reasoning for the basic biological categories.
Like mammal, herbivore, African species, the simple stuff.
Exactly. The simple stuff stays in OWL running super fast. But then they can write a separate, highly complex module in common logic to handle the complex part-whole relationships of the appetite in the tusks.
Okay, so they have two separate files now.
Right. Then they use DOL to write a formal link connecting the OWL module to the common logic module.
And because DOL is acting as the meta-language bridge, the computer system can actually read both simultaneously.
Yes. DOL gives that interoperability a formal mathematical grounding. The system treats them as one larger distributed ontology. It checks for consistency across the two different models, even though they are written in completely different formalisms.
Okay, I have to push back here. I am picturing this in my head, and honestly, it sounds like a recipe for absolute disaster.
How so?
Well, if DOL is a meta-language sitting on top, acting as a bridge, how does it actually know that a concept in a UML database means the exact same thing as a concept in an OWL ontology?
That is the million-dollar question.
I mean, how does it translate between two entirely different mathematical realities without making assumptions that corrupt the data? Because if DOL just arbitrarily drew string between UML and OWL like a detective's conspiracy board with a red yarn, it would just create a tangled web of spaghetti code.
It absolutely would. It would be chaos. And to understand how DOL prevents total chaos and data corruption, we have to open the hood and look at the underlying mathematics that connect these languages.
Right, the engine room. Let's get into the mechanics of this. From what I read in the sources, to tie these fundamentally different logics together, DOL uses a deeply theoretical mathematical concept called institutions.
I know, institution sounds like we were suddenly talking about banking or academia, but in formal logic, an institution is a mathematical structure that captures the commonalities across different logics.
You are going to have to go a layer deeper on that for me. What does a mathematical structure that captures commonalities actually look like?
Okay, the defining feature of an institution is that it captures the shared model-theoretic semantics of different languages.
Model theoretic semantics. Okay, I'm throwing a flag on that one.
I figured you would.
Yeah, break that down for someone who did not get a PhD in formal logic.
Think of model-theoretic semantics as the underlying physics of a language's universe.
The physics. Okay.
Even if two languages use completely different syntax, different words, different brackets, different symbols, they both ultimately exist to describe a mathematical model of reality.
Right. They're both trying to describe the real world.
Yes. They both have rules for what an object is, what a property is, and how objects relate to each other. By defining each language mathematically as an institution, logicians can map how the reality of one language translates into the reality of another, entirely bypassing the syntax.
I see. So it is not translating the grammar, it is translating the physics.
Exactly. It bypasses the grammar completely.
The sources describe this as a graph of logic translations. When I read that, I was picturing a massive, incredibly complex subway map where each station is a different logical language.
That is a brilliant way to visualize it. And the academic papers on DOL actually have diagrams that look exactly like subway maps.
Oh, really? So the analogy holds up.
It holds up perfectly. This graph maps out how less expressive languages, like RDF, or the various highly restricted OWL profiles like EL++3, DL Lite, or DLRL.
The local stops on the subway.
Right, the local stops. How they can be mathematically translated into more expressive logics, like first-order logic, common logic, or a language called CASL, the express trains.
So going back to our aunt and mother Annabelle problem, where the system crashed because you couldn't have an asymmetrical relationship and a property chain at the same time, how does DOL use this subway map of institutions to solve that gracefully?
Instead of forcing everything into one logic and breaking the decidability guardrails, you write the scalable, easy parts of your family tree in a basic, highly optimized OWL profile.
That is one subway station.
Right. Then you write the complex rule-breaking axioms, the parts that define how the ONT relationship is actually inferred, in a separate, more expressive logic module, like first-order logic.
Which is a totally different subway station.
Exactly. And finally, you use DOL to act as the tract between them.
And because DO understands the institutions of both languages, like the underlying physics of both stations, it knows how to map the simple OWL reality into the complex first-order reality without crashing the train.
Exactly. The reasoning software treats them as one larger ontology. It does the fast math on the OWL side and the heavy lifting on the first-order side, passing the necessary conclusions across the DOL bridge.
I'm thinking about this like gears in a complex mechanical watch.
Oh, I like that.
You have these tiny, intricate gears spinning incredibly fast. Those are the highly optimized, decidable OWL description logics. They are fantastic for quick, simple tasks.
Right, the local stops, the fast gears.
Then you have these massive, heavy gears turning very slowly, but with huge torque, that is common logic, handling the super complex expressive rules. DOL is the clutch system. It is the transmission that allows these totally different gears to interlock and transfer power without stripping their teeth out.
That is a fantastic analogy.
Yeah.
And what makes DOL so powerful is that its clutch system has different settings depending on what kind of mathematical connection you actually need to make between those gears.
Different settings? What do you mean?
Well, the standard supports different types of mappings. You have plane mappings, faithful mappings, exact mappings, and something called model expansive comorphisms.
Model expansive comorphisms. Say that 5 times fast.
I'd rather not.
Yeah. I am going to need you to unpack what a comorphism actually does for a developer sitting at a keyboard.
Let's focus on exact mappings and comorphisms because they are the most powerful. They mean that you can maintain different versions of an ontology in languages with completely different expressivities, and DOL guarantees, mathematically guarantees, that information isn't being corrupted when it moves between them.
Give me a real-world scenario for that, because that sounds like magic.
Imagine you have a massive financial regulation ontology for an international bank.
Okay.
You have a very simple version written in a basic language for your front-end customer portal, maybe just defining what a tax bracket is so the web page loads instantly.
Right. Keep it simple for the customer.
But you have a highly complex version written in common logic for your compliance officers, which details every single loophole and subclause of the international tax code.
It's a heavy gear.
Exactly. An exact mapping guarantees that if you prove a financial transaction is legal in the less expressive language on the website, it is guaranteed to still be true when mathematically translated into the more expressive language used by compliance and vice versa.
Wow. So it is not just a rough translation or a best guess. It is a mathematically proven alignment, which is staggering when you think about the sheer scale and consequence of the financial data we are talking about today.
It really is. It prevents millions of dollars in compliance errors. But having established the mathematical theory of how these logics interlock, the institutions, the model theoretic semantics, the subway tracks, we need to talk about how a human being actually uses this.
Right, because theory is great for academic papers, but software engineers need to actually compile code.
Exactly. Theory doesn't build databases.
So if I am a software engineer, what actual software is doing this translation in my terminal? Let's unpack the practical tech stack mentioned across all these sources. It seems to revolve around 3 main pillars: HETS, OntoHub, and a totally mind-bending thing called the LOLA ontology.
Let's start at the foundational level with HETS, which stands for the Heterogeneous Toolset.
The sources say HETS acts as the parsing and inference backend. It performs static analysis and proof management for DOL using something called CASL as an interchange logic.
Right. If DOL is the language that describes the bridge, HETS is the actual software engine that builds the bridge and tests its structural integrity.
Okay, so it is the compiler, sort of.
Yeah, kind of. When you write a DOL file that links an OWL ontology to a UML model, you feed that text file into HETS. HETS parses the code, checks the syntax, and manages the mathematical proof to ensure your mappings are valid.
And how does it do that? You mentioned it uses CASL as an interchange logic. How does CASL act as the middleman?
CASL stands for the Common Algebraic Specification Language.
Another acronym for the pile.
Yes. Think of CASL as the ultimate internal lingua franca for the HETS engine. Because CASL is based on algebraic specifications, it is incredibly flexible.
Okay.
So when HETS receives an OWL file and a UML file, it temporarily translates the underlying logic of both into CASL.
It pulls them both into its own sandbox?
Exactly. CASL is the mathematical sandbox where heads can compare the two, run the proofs, ensure the model theoretic semantics actually align, and then spit out a validated DOL structure.
Okay, so HETS is the engine room, running the algebraic proofs in the CASL sandbox.
Right.
Then we move up a layer to OntoHub. The OntoHub documentation describes it as a web-based repository engine that natively speaks DOL.
Yes. If HETS is the engine, OntoHub is the garage and the showroom. Think of OntoHub as the GitHub for these complex, heterogeneous ontologies.
Oh, that makes sense. A place to store and version control them.
Exactly. It stores all the structural information that HETS extracts from the DOL files. But more importantly, it exposes all that information to machines over the internet as linked data.
So it makes it searchable.
Yes. You can query this massive multi-language web of knowledge using SparkQL, which is the standard query language for the semantic web. OntoHub is what allows distributed teams around the world to actually collaborate on these massive DOL structures.
So we have HETS doing the math in the basement, and OntoHub storing and sharing the results on the web.
Right.
But then we get to the third tool, LOLA, which stands for Logics, Languages, and Translations. And this is where my brain started to fold in on itself while reading the sources.
I am not surprised. It is a very meta concept. LOLA is an ontology about logics and languages.
It is an ontology of ontologies.
Think about it this way. If DOL is going to automatically translate between OWL and UML and COM logic, the computer system itself needs a machine-readable dictionary that precisely defines what OWL is.
Right.
It needs to know what UML is, what their specific guardrails are, and what a translation actually means in mathematical terms. LOLA is that machine-readable dictionary.
And what is wild is that the academic papers detail how LOLA is built. And it turns out LOLA itself is a heterogeneous ontology. It eats its own dog food. It uses DOL to build itself.
It is the perfect showcase of DOL in action, because defining every logic in the world requires different levels of expressivity. LOLA uses different languages for different parts of its own dictionary.
The sources mention it uses RDF for its A-box assertions. I flagged that earlier because it sounded like total jargon. What on earth is an A-box assertion?
In ontology engineering, knowledge bases are often split into two parts, the T-box and the A-box.
T-box and A-box.
The T-box is the terminological box, that is the schema, the overarching rules. For example, every human is a mammal.
Okay, the broad rules.
The A-box is the assertional box. That is the actual data, the specific facts. For example, John is a human.
Ah, okay. Terminology versus assertions.
Right. So LOLA uses a very simple language, RDF, just to list its A-box assertions, the raw data of which logics exist, like OWL exists, UML exists.
Okay, simple language for simple facts. It uses a small gear for a small job.
Right. Then it steps up to OWL to define its basic vocabulary in its T-box, the rules about how those logics generally relate.
A slightly bigger gear.
But because we know OWL has guardrails, it isn't expressive enough to capture everything. So LOLA steps up again, using first-order logic to write closure rules that OWL can't express, like complex role compositions that define exactly how a translation mathematically behaves.
So it is stacking these languages together using DOL to describe DOL. It is brilliant. But then the paper mentions it uses one more thing, circumscription.
Ah, yes. Circumscription is used for minimizing the extension of concepts describing default translations.
Okay, I have to stop you. I'm throwing the penalty flag again.
I went too far into the textbook.
You cannot just drop a phrase like minimizing the extension of concepts and expect us to just nod along. Let's break this down. What is circumscription actually doing in plain English?
I apologize. It is incredibly dense terminology. To understand circumscription, we have to talk about two fundamentally opposed philosophies of how computer databases view the world. The open world assumption versus the closed world assumption.
Okay, I am with you. Two different philosophies of truth.
Exactly. The semantic web and languages like OWL operate on an open world assumption.
Which means what?
That means if a fact is not explicitly stated in the database, the system assumes it is simply unknown. It might be true, it might be false, the computer just doesn't know yet. The world is open, and missing information is expected.
Which makes perfect sense for the internet or for scientific research. If a side effect isn't listed in a medical database, you don't assume the drug is perfectly safe, you assume the side effect might just be unrecorded.
Exactly. You leave room for discovery. But standard databases, like the SQL database running a company's payroll or a police department's criminal record system, they operate on a closed world assumption.
And how is that different?
If a piece of information is not in the database, the system assumes it is definitively false. If you aren't in the employee table, you are not an employee. If a crime isn't on your record, you didn't commit it. The world is closed.
Got it. So you have OWL living in an open world, constantly expecting new data, and SQL living in a closed world, assuming it knows everything. How does DOL bridge that massive philosophical gap without corrupting the data?
That is where circumscription comes in. Circumscription is a logic-independent way of mathematically implementing that closed-world assumption inside a system that might otherwise be open. It is a form of non-monotonic logic.
Let me try to synthesize that. Circumscription is basically a command that tells the reasoning engine, for this specific module, I want you to minimize your assumptions. Stop guessing. If I haven't explicitly told you something is true, assume it is false.
You got it perfectly. It allows a heterogeneous system like Lola to seamlessly switch gears between open-world reasoning and closed-world reasoning without crashing.
Wow.
It gives the AI the ability to know when it is okay to guess and treat missing data as an unknown, and when it needs to treat the absence of data as a hard no.
That is incredible. It is essentially teaching a machine the context of truth.
It really is.
So now that we understand the deep theory, institutions and comorphisms and the toolkit, Hertz, OntoHub, and Lola, we can finally look at how a developer actually uses this in the real world to build things.
Which brings us to one of the most powerful applications of DOL, generic ontology design patterns, or GODPs.
Yeah.
We reviewed an incredible paper from our octave about how these patterns handle roles and change over time in complex systems.
Now, in traditional software engineering, a design pattern is just a reusable solution to a commonly occurring problem. It is a template you can copy and paste so you don't have to reinvent the wheel every time you want to build, say, a login screen. I assume the same concept exists in ontology engineering.
It does, but in generic DOL, these patterns take a massive, almost intimidating leap forward in capability. The paper notes that these generic patterns contain typed variables and parameterized names.
Okay, parameters. In a normal software function, you might have a function called calculate tax, and the parameter you pass into it is a simple number, like a salary of $50,000.
Right, but here is the kicker. In a generic ontology design pattern, the parameter you pass in is not a number, and it is not a text string. The parameter is an entire ontology.
Wait, what? You pass an entire worldview into a template as a variable?
Yes. Let's walk through a step-by-step hypothetical scenario to see why this is so revolutionary. Imagine you are managing the database for a global shipping network,
Okay, huge logistics operation.
and you need a design pattern to handle hazardous materials.
Okay, so I want a reusable template for how the system handles anything dangerous.
Exactly. So you build a generic ontology design pattern in DOL for hazardous materials. But the definition of what constitutes a hazardous material changes depending on whether the package is on a truck in California, on a cargo ship in international waters, or on a train in Germany.
Right. Each of those jurisdictions has a completely different regulatory ontology, different rules for what is dangerous.
So instead of hard-coding the rules for California into your global template, you leave it blank. You make the jurisdiction a parameter.
Okay, I am starting to see it.
Now, when your shipping software tries to route a package through Germany, it instantiates your hazardous materials pattern, and it passes the German rail regulation ontology into the parameter.
That is mind-bending. But what stops someone from passing the wrong ontology into the pattern? What if a tired programmer accidentally passes a bakery recipe ontology into the hazardous materials parameter? Doesn't the whole global shipping system just implode?
That is where the magic of generic DOL happens. When you build a pattern, you specify a parameter ontology. That means any argument you provide must legally, mathematically conform to that specific structure.
Oh.
If your pattern requires an ontology that defines chemical volatility and flashpoints, you cannot pass an ontology about baking bread. It will reject it.
And HUTS, our engine room from earlier, is the thing that checks this conformity.
Yes, and it checks it statically at expansion time.
Statically, which means it checks it before the software actually runs.
Exactly before execution.
It is like static analysis in programming languages, where your code editor underlines a syntax error in red before you even hit compile, but for complex semantic logic.
Yes, the heads engine proves that your logical assumptions are mathematically valid before it allows the data to be integrated into the live shipping network.
That is a total lifesaver for data scientists and systems architects. You catch the logical fallacy before a truck full of chemicals is illegally routed through a residential neighborhood in Berlin.
Exactly. And the sources also highlight how this completely revolutionizes change management over time.
Oh, absolutely. Managing change in a massive multi-language database is a nightmare. Usually your log files have to contain every single tiny data change, every single new row added to a table.
It generates terabytes of useless noise.
Mm.
But if everything is based on these rigorously checked generic ontology design patterns, the log file doesn't need all that noise.
What does it log instead?
The log file can just contain a list of GODP instantiations. They become the basic atomic units of change.
Okay, let's play that out. Let's say the European Union updates its foundational regulatory ontology for what constitutes a hazardous chemical.
A huge systemic change.
Right. If your global shipping network is built on DOL patterns, your log file can simply be replayed by the system.
Because DOL understands the underlying logic of the patterns, yes. It takes that new EU ontology, passes it through all the parameters, checks the static math via HETs, and automatically distributes the effect of that regulatory change across your massive, heterogeneous global data sets safely.
It updates the whole world's logic in one fell swoop without breaking the SQL databases or the OWL semantic webs attached to it.
And that is the raw power of parameterized ontology.
So let's bring all of this together. We have gone incredibly deep into the weeds of mathematical logic and software architecture today. But let's connect this directly back to the listener. Why does this matter to the average person?
It is a fair question. Let's look at the broad usage scenarios outlined in Section 7 of the DOL standard, which AWS specifically highlighted in their presentations on interoperability.
The standard points out that DOL enables interoperability between closed world data, like a highly secure corporate SQL database, and open world metadata, like the semantic web.
Right. It allows for coherence checking across entirely different UML models built by completely different engineering teams.
What this means is that behind every seamless digital experience you have in the modern world, there is a desperate need for disparate, fundamentally incompatible databases to talk to each other without losing the precision of their original designs.
Exactly. So the next time you track a package from a factory in Shenzhen through customs in Seattle, onto a train to Chicago, and into a delivery van.
Think about the dozen incompatible databases that tracking number just passed through.
Or consider the frontier of bioinformatics and drug discovery.
Oh, that is a huge one.
Developing a new targeted cancer therapy requires integrating genomic data, massive chemical databases, real-time clinical trial records, and historical patient family histories.
And those repositories were all built over decades by different scientific communities using entirely different logical standards.
You can't just mash them into an Excel spreadsheet.
No, definitely not.
DOL provides the mathematical framework that allows an AI to look at all of that data simultaneously, understand the specific logical context of each piece, and draw accurate conclusions without making mathematical fallacies that could cost lives.
It is the ultimate translation matrix. And if it is doing its job perfectly, it is completely invisible to you and me.
Which is exactly how good infrastructure should be. You don't think about the structural engineering, the tensile strength of the steel, or the wind shear calculations when you drive over a suspension bridge. You just trust that the math holds up.
DOL provides the math that holds up the bridges between our digital worlds.
I could have said it better.
We have covered a massive amount of ground today. We started by exploring the crisis of the Tower of Babel, the limitations of single language systems where trying to force everything into one language, that whole Esperanto approach, either breaks your decidability guardrails or slows your system to a crawl.
Right. Then we discovered how DOL flips the script. It acts as a meta language, a Rosetta Stone. It links everything from UML to common logic, using the deep mathematical concept of institutions.
Mapping the model theoretic semantics of different realities so systems can share information without losing their native structure.
We looked at the practical tools that actually execute this theory. Heats acting as the algebraic engine, OntoHub acting as the linked data repository, and Lola, the mind-bending self-referencing dictionary of logics that uses circumscription to juggle open and closed worlds.
And finally, we saw how generic ontology design patterns use entire ontologies as parameters, statically checking the logic to guarantee data integrity across massive global systems.
It is a lot to take in.
It is. But even if you never write a single line of code or engineer an ontology, understanding that this infrastructure exists is crucial. We now have a standardized, mathematically proven way to integrate fundamentally different logical realities.
The AI of tomorrow will not just be scraping text on the internet. It will be reasoning across heterogeneous logical models. It'll be drawing deep, verifiable conclusions from systems that were never designed to speak to each other.
And that leads us to a final, slightly provocative thought to leave you with. We spent some time today unpacking circumscription, how DOL allows machines to seamlessly bridge closed-world assumptions, where anything unknown is considered strictly false, and open-world assumptions, where anything unknown is simply a mystery waiting to be solved.
Right. It teaches the machine to hold two different philosophies of truth simultaneously, depending on the context.
So if our computer algorithms can now smoothly navigate, translate, and reconcile these two fundamentally different philosophies of truth, what does that mean for us?
I see where you're going with this.
Human organizations, governments, even individual people often operate rigidly in just one of these mindsets. We are either rigidly closed world, demanding absolute documented proof before accepting a truth, or trying a new idea.
Or we're open world, constantly adapting to new unknowns, but sometimes lacking strict boundaries.
Exactly. If the machines we are building to run our societies can now fluently speak both languages of truth simultaneously, how might our human institutions need to adapt their rigid mindsets to keep up with the systems we have created?
It is a profound question. At the start of this deep dive, we talked about that medical x-ray, a clean, binary reality. Broken or not broken. Closed world.
But human knowledge isn't really like that. It is muddy, it is complex.
What DOL gives us isn't just a better x-ray machine. It gives us an MRI that can translate the dense, rigid bones of closed-world databases and the complex soft tissues of open-world semantics.
And fuse them into one perfect, highly readable, multidimensional image of reality.
The muddy waters are finally clearing up.
Until next time, keep diving deep.